Okay, everyone, I think I'm going to get started here. I'll be switching today between PDF files and some videos. So if I don't start sharing the appropriate stuff, do speak up and let me know. We'll be covering kind of the theory or applications of the second part of the 2-hour lecture on, the second of the 2-hour lectures on GANs before we move on to the homework and collab notebooks associated with GANs. And this is kind of a combination of some theory and example applications of GANs. So again, the best thing to do would probably be to go through the papers that are referred to in the discussions. I haven't had the time to go through them myself. So just as in the lecture, this will be more of an introduction without a lot of the technical details of those things. Because I think even in the class, they just point to it and kind of highlight the relevant things about what these different papers and their associated techniques and or examples do. So that's kind of what we are going to go through. And we'll also reach back and cover something that I had to skip in the interest of time and which becomes relevant now, which is kind of the concept of mutual information. With that said, it's going. Let me know if you folks can see the PDF that I'm sharing, the slides.
Yes, we can see it.
Okay, great. Okay, so last time where Morten left this in the lecture was kind of the first version of style GAN and some addition of noise which helped the images look a little bit more natural. For example, why that is and stuff hopefully was covered in the paper description, but that was one of the things that was illustrated at the end of last lecture. And what this lecture starts off with is how the researchers at NVIDIA kind of then came up with style GAN 2, where they work on a lot more detail and making the image even more realistic and get rid of some very nuanced or very detailed effects, so that at the end of the process, we get very realistic photorealistic images. And also in the process, they've enabled a bunch of applications of GANs towards graphics and towards artists using it for a variety of purposes, which we'll see as we go through the rest of the lecture. So the thing here, the first artifact that they kind of focus on in style GAN 2 and try to eliminate, and then we look at a summary video at the end once we go through kind of an introduction to some of what they have done and why they have done it, is something called a water droplet artifact. So as you can see in this slide, in the images, there are these little tiny dots that are there in the image. Interestingly, it's there apparently in all of the images. And the other thing that these guys figured out is that it's there not just in the final image produced by the GANs, but it's also there in much of the earlier layers and activations as they go through the GAN. So the focus was in removing it. And you may ask, is it just a fact that they want to remove it because it's an artifact and they don't like it and they would like the images to be photorealistic, as I mentioned, but there's also another motivation for getting rid of these kind of artifacts that persist, right? And that is the fact that in a GAN, obviously we are trying to discriminate, the discriminator tries to discriminate between real and generated or fake images. And this could be one of the ways the discriminators can cheat. If it learns that there's always this, water droplet artifact, then it could kind of, as soon as it detects that, can say, hey, this is fake. So that's another motivation to kind of try and get rid of this particular artifact. So what they do, in a sense, and again, Moten had touched on it, there is in these traditional style GAN, the style vectors come in, and then there's something, I haven't again gone through the details, it's probably there described in the paper, but there is this adaptive instance normalization that happens. It's another variation of normalization, and originally they'd done this adaptive instance normalization, and the location of it in the pipeline is that the style vectors which are coming in here modulate that, and then there is a convolution that happens. Now, instead, what they do in the and the details of it are, the convolutional filters have the weights and the biases. Then the style GANs are these A things that are coming into the style GAN and basically the style block, and the feature maps are coming in from the top, and the first level parameters of the feature maps, such as the norm, mean, and standard deviation, are computed in the style GAN. Now, the modification they make, and in the lecture he says, hey, it's somewhat kind of empirical in the sense that why they do this and why this results in the better and elimination. Maybe they explain it in the paper, but at least the lecturer seems to think that it's not intuitively obvious as to why this particular modification ought to be able to get rid of the watermark or the water droplet artifact, but nevertheless it does. And the modifications they do is, instead of computing both the mean and the standard deviation of the feature maps that are coming in, what they do in the enhanced or style GAN do is only compute the standard deviation, and they don't do anything to the mean. And then they bring in the style GAN, then just modifies or comes into this what they call the model standard. But in effect, eventually, when they're all said and done, what they're doing is only change in sigma, or at least the standard deviation of the feature map. And instead, these style vectors, which went into this adaptive instance normalization, there is no adaptive instance normalization in the new revised architecture. There's this thing called weight demodulation, where the style vectors come in and modify the kernels that go into the convolutional filter, and that is what happens within the style block, and only the scale of the input feature maps is changed. And once these modifications are implemented in the style block, and obviously, there are a couple, three more changes they do, and then this is again a high-level superficial explanation. You'd have to read the paper to get into the nitty-gritty details. But this change, which they call weight demodulation, helps them solve the issue of the water droplets. So that's one particular issue that they resolve and help make style GAN 2 much more photorealistic without the water droplet artifact. The next thing that they talk about is actually easier and to explain when we look at the video, and I'll switch to that, but give you the explanation here before we switch to the video. But what they talk about is they use the style GAN to operate on what are called flicker faces high quality data set. And these are images, I believe, of people that are of very high photo resolution like quality. And one of the techniques that is applied in style GAN is this progressive growing, and that's similar to what I think in past AI and others, especially Jeremy, the teacher, talks about, progressive resizing. So this is progressive growing. And when the progressive growing is done in order to get the final results, that in turn apparently leads to some specific artifacts. And you'll see that artifact when we look at the video, but the artifact is something where, for example, if there is, and the artifact is much more visible when you see sequence of images of a phase as you produce the, obviously they show it at the same resolution, but apparently it happens when you are growing the image in order to get to the full size. And the effect that happens is something where in the original image, if there is some aspect, like for example, if the face is looking at a particular direction and it changes, if the face were to change over time to over a series of images to look in a different direction, and you focus on the eyes, for example, then they are in a particular location for a substantial portion, and then suddenly they jump to the final location. So in that sense, if you're generating a progressive growing and stuff, there isn't a sequential movement, or there isn't this continuous movement of the eyes, which is what you would expect, so that, at certain parts of the growth, your eyes don't seem aligned with where the person is supposed to be looking in the picture. And we'll see that much better when we look at the video. And that is something else that they address in terms of trying to make the StyleGAN much better. So the point of introducing StyleGAN version 2 is to say that I think that the NVIDIA researchers have kind of got StyleGAN 2 to the point where it really produces excellent quality images. And as the lecturer says, if you really need high quality images produced by machine learning with a lot of latent structure, then the method that you ought to seek out or go to as the preferred method is the StyleGAN version 2. And similarly, if, for example, you're looking for something which produces excellent class conditional images, and by class conditional, we mean, if there is a horse in the image and the class is that of a horse, so you always want a horse in an image, or whatever class that you happen to seek, then the best class conditional image generator is what Moten covered last lecture. That's the Big GAN. So we have kind of two go-to techniques that are kind of state of the art, at least as of when the course was taught, which is a couple of years. I have not looked into whether any major changes have happened since then in the last couple of years, but given that these outputs were excellent, there might be some tweaking towards the edges, but I'm not sure that they have fundamentally changed. So the go-to techniques, if you want high quality photo resolution images, are StyleGAN 2. And if you, especially if there's a lot of structure in your image at various levels of resolution, and then if you want best in class conditional image generator, what you seek out or go to is this thing called the Big GAN. So with that said, let's see whether, so the next concept we'll get into is this whole information bottleneck and how that's applied with respect to GAN. So now I'll switch and we'll look at the video. I particularly turned off because there are some volume issues and other issues with my computer. So we'll just look at the video without any volume. It will just play and I'll talk to the various techniques or things that you will see in the video. We've already kind of touched on it, but nevertheless, let me switch. Can you folks see what's on my screen? Or Yes, no? Anything?
Yes, we can see.
So you can see here, can you see the face?
Yes.
Right.
Yes,
So
we
you'll
can.
begin to see the artifact, the droplet artifact that you're talking about. That's the interesting thing is they show, before we get to the next step, the interesting thing they show in this is the fact that you can see it at even a 128 by 128. So apparently they point out that, you can see it all the way down to 64 by 64. So it's not just there in the final image, it's there in the activations of various levels of image. Then we talk about, the second effect that I was talking about in highly structured, the flicker faces. And you can see that what they try to point out and the blue lines seem to indicate, if you focus on just that particular feature, like her eyes, and if you look at as the face orientation changes, you'll see that the eye stays in the same direction until the face is completely moved to the new pose, and then the eye snaps at some point. And again, that is not, so in fact, because this is not video, it's just actually frames. So what they're trying to illustrate is that the GAN doesn't produce the right eye location or eye the direction in which the pupil should be pointed to as the images are generated, because it's not consistent at some parts when certain images are generated, and that's something else that they fix. And you can see that, at this point, her left eye here is, her left eye is, but this right eye hasn't shifted. And then suddenly you'll see, as we go through the video, that it will snap to what would be a more proper location for the eye. And it's the same thing with the teeth. The teeth remain in place. The orientation of the teeth, they have kind of shifted with respect to our nose. They should be a little bit more on the, different direction. And you see that now. You can see the eye moving towards where it should be pointed to, consistent with the face. And it's the same thing here. This should be located more to the right, but that hasn't happened yet. And again, yet again, the reason for it is it means that certain images, if you're changing the pose, will not have the proper eye or the proper teeth locations. And that's, again, something that the discriminator can catch and can therefore decide that the image is fake. And that's something we want to, or at least these folks, focused on and help fix this issue in StyleGAN 2. So very, very unique detail, most of which at least many of us probably would not be able to catch, but something when you're generating photorealistic images that people who are trained in the art will immediately discover. So you can see that now her eye is snapped. And instead, if you see in these images that are more generated using StyleGAN 2, you do not see that effect. It seems extremely natural as it happens. Right? So the eye moves in a very continuous and smooth manner. And then they go on to talk about other things which cover as part of the lecture. Okay, back to our let me know if you can see the PDF.
Yes, we can.
Yes. Okay, thanks. Okay, so the next kind of concept that the lecture introduces is one of information bottleneck, and how to use information bottleneck in combinations with GANs. So this is GANs operating on not the actual final image, but GANs operating with a latent variable model, right? So think of it this way, that instead of the GANs where Mosenet covered last time, where we feed the generated image and the actual real image, instead of that, think of feeding a latent variable instead of the actual full image to your discriminator, right? And you do that for the output of the generator as well as for your true image. So both of them go through an encoder, which puts both the generated image and the actual real image into a latent distribution. And that is what you feed to the discriminator. So the discriminator now takes in some inputs in the latent space, right? So the discriminator, in effect, is deciding between real and fake, not in the original distribution space, but in the latent space. Now you could kind of say, why is this useful, or in what way is this a variation or a change, and why is this likely to help? Well, one reason explanation that we can think of is the fact that when we put this data in a latent space, then obviously we are reducing the space. The latent space is, as we have seen many times before, is with a much smaller dimension than the full image. So in effect, what that means is the latent space tries to abstract some of the key information in the original dimension, and therefore the discriminator is less likely to focus on spurious things within the image and has to focus on some of the key things that are captured in the latent space, right? That in turn will help the discriminator play a better GAN game than when we are operating in the original space, or at least that's the thinking behind this couple of papers. The variation information bottleneck concept, and then a GAN that's based on the variational information bottleneck concept. So the motivation to do this is by putting these images into a latent space, we try to make the discriminator play a better GAN game. And now, one of the ways that this effect will actually result in something better is if it ensures that the latent space is not the same as the original image space, right? Because if that's the case, then we haven't done anything. So we do want the latent space to be actually latent, and which means that it has a much smaller dimension than the original image. Now, in an autoencoder, obviously, you map the original image into the latent space and then regenerate the original image, right? So that's kind of why we refer to it as a information bottleneck, because we are kind of mapping it into a space with much lower number of variables or latent vectors, and then bring it back to what it used to be. Of course, in auto encoders, we bring it back to the original image. Here, that isn't the point. We feed both of these having gone through an encoder into a discriminator. So the point here is when you bring in this concept of information theory into the realm of kind of the GAN setup that we have, and make sure that the latents do not have all of the information that the original data has, then that's kind of what the information bottleneck GAN is. Now, that then brings us or introduces us to a necessary concept, which we, as I mentioned, I had kind of not, interest of time, not touched on, but it's relevant here, so we will touch on it, which is the concept of mutual information. So that means that in order to make sure that the encoder really does, or stated negatively, really does not include in the latent all the information that is there in the image. So what you want is not all the information in the latents that is present in the image. You want the latent to be in a much smaller dimension. That means that you want to limit the amount of mutual information between the information that's contained in the latent and the information that's there in the original input. So between the original input and the latent, you want to limit the mutual information content. So let's then step back and understand a little better what mutual information is. So again, I'm going to switch to a different tab. Let me know if you can or cannot see this. Can you see the mutual information header?
Yes. Yes. We can.
Okay, thanks. So here's the concept of mutual information. So mutual information between two random variables, and that's I between the two variables X and Y, is defined as the entropy of X. And from that, you subtract the entropy of X given Y. And it kind of makes sense if you think about it for a minute. So if we know Y, right, then in what way is the uncertainty of X reduced? Well, the uncertainty of X as a whole is this orange circle. If we know Y, then we know this part already, and therefore the uncertainty left in X when we know Y is this guy, H of X given Y. So if we subtract that from the overall uncertainty of X, then we get the mutual information between X and Y, right? So the mutual information between X and Y is the entropy of X, that's the uncertainty of X as a whole, and from it you subtract the uncertainty of Y given X. Similarly, you can flip it around and make it work, symmetrically with respect to Y. So it's the mutual information of Y, the entropy of Y, and from that you subtract the entropy of Y given X, and you end up with a mutual information between X and Y. Now, why is this concept useful? In what way is it useful? Now we are about to see the application of it in the InfoGAN and so on. But here is the also interesting insight as to why this mutual information concept is kind of somewhat insightful. If you look at just the expectation of Y with respect to X, right, between two random independent variables, and if you just think of the first order, such as the covariance, what happens is this is the covariance between X, this is just the variance, and then you look at the covariance and you look at the expectation of Y with respect to X. For all of these at the bottom, the expectation of Y with respect to X is 0. But the interesting thing is that the mutual information of X with respect to Y is not 0. So for example, if you were to, take a point that's here or a point that's here, or a point in the center, you definitely know which is X, then you definitely know something about Y, because either Y is here or Y is here. So similarly for a lot of these kinds of variations. So the point being that the concept of mutual information gives us some information about X if you know Y, or Y if you know X. That's not what on the average the value of Y if you're given X would be. So the mutual information provides something more or something new when compared to just the conditional expectation of Y with respect to X, or X with respect to Y. And where that is useful, we are about to see that is in concepts. We'll see InfoGAN towards the end of the lecture, but we are also beginning to see the application of mutual information, right? And apparently, for those of you, I think, like mine, and one are familiar with reinforcement learning, apparently there's some application in reinforcement learning setting as well, where we want to maximize dependency between two variables, or do a better job of estimating the dependencies. And what he is now, and we'll see the application of exactly this here, it seems a little bit more theoretical, but when we look at it, we'll see the exact same equations crop up again. So in effect, what we can try to do, and in fact, in this particular example we're looking at, we will be applying exactly this technique, which is, let's say we want, and here again, let's say Z is the latent and X is the original. If you want to maximize the mutual information between, say, Z and X, then given that this is the equation, given this guy, Z, the entropy of Z given X, we again go to our, and we use that in implicit latent models, go through add and subtract the variational distribution. So you get from here to adding and subtracting the QZ, and then change it into, oh, one of these is a KL divergence. And once it's a KL divergence, then we say KL divergence is always greater than or equal to 0. Therefore, this becomes greater than or equal to sign. And this expectation is what we are left with. If we are trying to maximize the left-hand side, that means given that this is, not something that changes, we want to minimize this expectation. So, and this in turn is nothing but training a good classifier going from X to Z. And so if we, in order to maximize the mutual information, what we have narrowed it down through all this maths is to say that what we want to do or get from our neural network is a very good classifier that goes from X to Z, and we have achieved the objective of maximizing the mutual information between variables. Right? So that's kind of this little bit of a concept that we had not learned or skipped when we did the previous lectures. So now we learned that concept, we are back to our information bottleneck and this mutual information related concepts and information theory concepts. So what is the situation is, if we enforce the fact that there is an upper bound on the information or the mutual information that's shared between the latent model and the original X, then that helps us kind of achieve our goal of creating an informational bottleneck. So that's what this means, that the mutual information between X and Z, we want it to be bounded. So we want not all of the information of X to be present in Z. We want it to be bounded by some amount. So the mutual information is to be limited so that the latent is a subset, if you will, of information that the original image contains. Right? And then this paper apparently discusses how to achieve that with stochastic gradient descent and so on. Now, the thing is, if the KL divergence between a couple of Gaussians is apparently unbounded, meaning that it can be even up to infinity. But ensuring that we have this threshold makes sure that we limit it. So now, obviously, if it's an upper bound, then this thing could just be infinite, meaning that, there's no, as long as it's an upper bound, then, it can continue to, a lower bound, then it can be infinity. So in effect, what we begin to treat it is that, hey, this is an upper bound on the mutual information. That is, we want the mutual information to be less than some value, right? In effect, all this math, eventually what it turns into is the following set of kind of, in one dimension, this is how to understand what all this math of ensuring that the mutual information is less than a particular value accomplishes. And in the next several slides, we'll kind of try to get an intuitive grasp by looking at what this concept or approach does in one dimension. So he says that this is eventually equivalent to a KL, an encoder that we put the X input into, so we generate a latent with respect to X, and the KL divergence between that and the prior is less than some threshold, and the details are in this paper. In a one-dimensional model, if you will, or a one-dimensional visualization of this, what he's trying to explain is when the real and the fake data are separated by some distance, then what happens is the discriminator is learning what is essentially a kind of unit function, right? And So you don't get any gradient of this with respect to your fake data. And this is one of the reasons that in the paper of called the instance noise, that some noise is added to the instances so that there is some overlap generated between the real and the fake data. So it, we get a better gradient than this unit function, right? In the so the GAN game in effect is played better, right? So that's one of the reasons we add noise to the input images and to the various features and making sure that there is some overlap between the real and the fake data. Now, in the variational information bound scenario, right, this, what we are, again, in a one-dimensional case, what he is trying to illustrate is something that imposing a maximum mutual information threshold causes in the multi-dimensional case to happen. That is, you bring the latent and the original input somewhat close together, but limit how much overlap or how close they are in their respective dimensions or spaces. So in effect, the variational information bound approach or the VIB based GANs, what he's trying to explain, what the effect of them is to bring the latent and the real image closer together in dimension peaks, if you will, in the respective dimension, in order to create some overlap, leading to a better discrimination GAN game that gets played. Right. So this is again the effect of enforcing a threshold of sharing between the X and Z. So if we don't, then one extreme is this unit pulse-like thing, and the other extreme is this could end up completely being overlapped, which is not good either, because in that case, the latent isn't really giving you anything in a less dimensional space. It becomes the same as much information as your real image. So you bound it by this, ensuring some overlap, which in turn results in a better and a smoother gradient, a better GAN related output overall. So that's kind of the concept of variational information bound GAN. And that's to create this overlap between the real and the fake data in the latent space to create this. And that's the paper that I believe way back here. This is the second paper that he refers to, the variation information bottleneck GAN. Okay. Any questions so far? Okay, the next concept then that's introduced is something called creative conditional GANs. And here again, there are some very interesting applications that they refer to and kind of give some cool examples of how the conditional GANs or pix-to-pix, as I think it's known popularly, is something that is discussed, including its various applications. So let's look at what conditional GANs are. The conditional GANs, so the basic idea is if you have an input image and the idea is to modify it in some way and then produce a new version of that image. So for example, in this case, a black and white image is converted to a color image by going through the generator in the GAN. Okay, so here's a black and white image on the left, a color image on the right. You take it to the generator, and you're getting a nice colorized version of the black and white image. Now, given that I'd already mentioned to you that the class conditional GANs give you real good quality images, this is obviously a high quality image. Now, there are various ways in which you can train this. He talks about, for example, the MSE laws. Then you can treat each of the pixels as a Gaussian independent of the other pixels. You can treat it as a conditional pixel CNN and so on and so forth. But one of the ways that we are focused on learning, because there is obviously a lecture about GANs, is how we can use the GAN setup in order to generate this kind of conditional GANs, that if you provide an input, take it through the generator, and you get some modifications of the input that you're seeking. And conceptually, at least, this is where you begin to see the power of the application when you start thinking in somewhat of an abstract way of how to apply GAN. So in this case, I'm showing you a color modification from input to the output of the generator. You can think of many different translations here. One is color, another could be texture of the image. Another thing could be you draw the edges of certain things, and then you have an actual real person. So you can like sketch the outline or edge, and you can get a real image of a person or a generated image of a person, if you will. Then you can, and we'll see all that in the videos. I just want to kind of verbally introduce the concept here. Then you can also apply this to videos. So you begin to generate videos. If you have input videos, then you begin to generate output videos, but the output videos are not exactly the same. You can modify them in certain ways. If you have a source video, you can modify it to generate a new set of videos. And this is where, a lot of the deep fakes and these kinds of things are generated. So you can have some faces and then have other faces or generated faces doing the same thing as what the original face would do, things of this nature, which we see in videos, right? But because the GANs are good at producing high quality, high resolution images, and so using a GAN to kind of do these things are interestingly very interesting applications of the GAN technology. So in practice, while there is tremendous amount of detail currently in the paper, as I mentioned, I haven't gone to the paper itself, but it just introduces the key concepts in the lecture. So what we want in the setup right now is, in a GAN setup, is you take a black and white image, push it through a generator, and then we get the output of the generator, which would be a color image. And we want to push that into a discriminator and have the discriminator tell us, is this real or fake? And obviously, we'll need to feed a bunch of color images to the discriminator to help it to train it in order to see whether it's real or a fake. So we'll obviously need a bunch of real color images. So the setting, if you will, is similar to that of a GAN. So the difference is that instead of taking the Z variable, which, to our input to our generator, which would have been kind of, you start off with some Gaussian distribution and then take it here, we take an additional input, which is the actual image, and get that into the generator. So that's kind of what happens here. So we have an actual image X, a latent vector Z, and the generator G uses both the actual image and the latent, which is typically only thing that is provided normally. So G tries to synthesize the fake images that fool D, and then obviously G tries to identify the fake. That's our GAN setup, right? So now the GAN equation, if you will, is this traditional equation, is this equation that we see in the bottom. Now you feed an image, you get the G of X, and you get a Y, which is a colorized, and then you kind of train, and in some cases it will say, oh, it's not colorized, so it's fake, it's colorized, it's real, as it's fed images which are colorized. But, and this is the interesting point, in fact, the first interesting point about this setup is the way conceptually that we get to think about it. Conceptually, what it's doing is we are kind of making the generator optimize some perceptual loss, right? In this case, it happens to be the setup we are thinking about is that of the generator creating color images from black and white images, right? And in which the discriminator is learning what is real and fake. And if we just focus on color, it will say if it is not color, then it's fake. If it is colorized, then it's real. And using what the generator is doing is it's learning the discriminator's loss function as its loss function, right? So in a sense, it's learning to optimize its output for the loss function of the discriminator. And that is what is the basic idea that can then be used in a GAN network to do the many things that I talked about, like from edges or generate faces, from very crude paintings, generate real photorealistic images, and so on and so forth, right? Turning edges into an actual image, colorization, blah, blah, blah. And this concept of the generator learning the output optimized based on the discriminator loss function, right, is better than just having output of something like the generator trained on an MLE loss or a maximum likelihood estimator. So conceptually, what this setup is telling us is, hey, if the generator were to learn a loss, which is actually corresponding to the loss of the discriminator, that's better for us to get what we want. And that's kind of the insight that these people had with respect to utilizing the GAN setup to generate these kinds of new outputs from a given input, right? But as currently set up in our, if we continue to use just this equation, if you will, the traditional GAN equation, and if we just have this kind of a setup, there's a fatal flaw in why this particular setup will not work. It's a basic fundamental issue. Any ideas, thoughts on the mode or why something like this setup exactly would fail? I mean, once we get into the next few slides, it becomes very obvious, but it's kind of very fascinating as to think about why such a setup would fail to give us the result we seek, or at least there's a very simple mode of failure. Any thoughts?
The optimizations, I think so. The gradients that will flow backward will depend upon the realness of the discriminators choosing. So if we architect our simple neural network like this, then it's bound to fail due to that reason.
Maybe, but actually there is a simpler reasons why this fails. And actually I didn't catch it either, but once I reveal the next slide, it becomes very obvious. And it's kind of as, the humorous thing is it has to do with cats. I mean, very obliquely, or kind of it can have to do with many other things, but think of a colorized cat image instead of this bottle image here. The discriminator will still tell you that it's a real image as currently set up, right? Because all it's looking for is whether this image is colorized or not. It's not looking for whether the image has bottles and stuff. How will it know? It only is looking for colorized images. That's all. You're feeding a bunch of color images to the discriminator as it's currently set up. So in effect, what happens is it fails in, so again, this is something that I've already explained, that G's perspective, D is a loss function. And so instead of being hand designed, which is what we do in MLE, here we learn it. That is in the interesting part. This is the interesting part. But suppose this image were to be a colorized cat, and we then ask it to decide real or fake, it will say real, because this is colorized. And what we have fed as reference a bunch of images are all colorized images, and this is colorized too. Now, there's no way this guy knows what's in the content of the image, right? So what we need to fix in the traditional GAN equation to get it to work like we want it to is not just the output of the generator, but the input going into the generator too, because it needs to understand what is in the source image. Then the discriminator, we can say, oh, I have what is in the source and it is colorized. Therefore, now I'll be able to say, is it real or fake? Paying attention not just to the color aspect, but also to what is in the original image. Does that make sense? So it needs to decide whether the pair of inputs that's given to it is real or fake. The pair meaning the output of the generator and the original input of X. So what happens in these conditional GANs and the pix to pix is they need to modify this guy and this guy here. So that's what we'll see in the next slide. You see that, yeah, so he's just saying, hey, this as set up previously, which is kind of not the correct setup, it will decide, the discriminator will decide just based on the colorization, oops, it's real. And that's not what we want. Therefore, we feed to the discriminator a pair of images. I mean, it kind of, to me, it's not an, I mean, don't think of it that way. I'm just saying that it's like a Siamese network or whatever. In this case, you're giving it two inputs, the original input of the GAN and of the generator of the GAN and the output of the generated image from the generator in the GAN. And then you decide, is this a real or a fake, not single thing, but a pair. So you can see as compared to, yeah, as compared to just having g of x, here you'll need log of d of g of x and x, and here log d of y and x. See that? So those are the two modifications that are needed in the conditional GAN setup. As it so happens, as with many times in practical empirical applications of things as opposed to theory, there is also something else that they add, I think, in the conditional GAN. So the basic thing is you take the input and the output of the generator and feed that both to the discriminator. So the discriminator now gets a pair, and we have to decide whether it's a real or a fake pair. This is the conditional optimization GAN function, right? So the discriminator in case of the conditional GAN is a kind of dual input, decides on pairs. And in addition to this, they also add, and there's just an explanation that, given a cat, it will decide that it's false pair, and given the model image, because that's the black and white and there's the colorized, it will decide that that's a real pair. And that's a fake pair. And so that's what you make the changes. But in addition, oops, sorry, took it fast. There's one additional term that empirically these guys who did the conditional GAN paper have also added, and that refers to this term, if you will, is an L1 loss term for the output of the generator, and then when you're adding the two losses, you multiply that by some lambda. The L1 loss of the output of the generator is an indication of the quality of the output image. So not only are you focusing on and providing these two inputs, you're also focusing by the addition of this plus lambda L1G term, the quality of this guy, the generated output from the black and white image. So you're focused on, hey, is this a colorization of this image? And is this a high quality version of the colorization of this image? So that's essentially what this conditional GAN loss function conversion is, right? So that's kind of what they end up with as the loss function of the conditional GAN. And in addition to this change, there is some other changes that the conditional GAN or the pix-to-pix paper makes in order to make the result be much better. And that is the concept of making the discriminator somewhat weaker, that is shrinking the capacity of the discriminator. And now the way they do this, apparently in the Pix-to-Pix paper, is to make the discriminator not focus on the entire image at one time, but focus on different patches of different size from the image. And that is one way. Actually, they do 2 or 3 different ways apparently in the paper, but here he discusses one of them, which is shrinking the capacity of the discriminator. So instead of taking the whole image, you take patches from the image that is produced. So for example, you take the patches from the colored bottle images, and rather than penalizing if the output image is fake, you penalize depending on the overlapping patch, right? If the output looks fake. And that's yet another detail that they implement. And they show, if you're looking at a discriminator in the 1x1, it's kind of, again, I didn't quite completely understand. And for that, I believe we'll have to look at the paper. Obviously, we see that it is, the discriminator is, you don't see as much of the features from the original image when you're just looking at these patches. Oops. Whereas when you're using a larger patch, a 16x16, you can begin to see a lot more of the features of the windows. And so you can chunk or figure out patches or chunks from the image and then do the comparison. It gives you multiple advantages. You have fewer parameters because the patches are obviously much smaller than the entire image. Because you can provide many more patches, obviously there's just a single image, but then you can provide many more patches. That leads to this more supervised observation, which means, you know what the desired output is for patches, which means you have many more supervised patches. And then the other thing which they kind of figured out after applying these techniques and as a result of the paper is the question that's open is this technique good enough to be able to work at larger resolutions of the image overall, or does it only apply to a small number of classes and smaller images? And the answer empirically that they determined, and of course, by the way, again, word of caution, these are not the only techniques that are applied in the paper. Apparently, there's a bunch more of details that they apply, including various principles from graphic domains and so on, in order to make sure that the output is of high quality and it matches what graphic artists would normally expect from these outputs. But once all of that is done, then you can really get high quality images and can do a variety of different cool applications that we'll begin to look at in a minute. So we'll just kind of scan through it and then look at the video of it. But basically, if you have, let's say you draw an outline picture of a cat, such as these 3 things, a conditional GAN, once it's been trained, can then fill in the texture of these cats. So you just sketch this and you get the output back, right? Which is fairly cool application. So artists can make very basic sketches, and from that they can get photorealistic images. And then you can just let your, imagination fly, because actually, apparently, Adobe has products based on these kind of techniques where it colorizes black and white images, and that's they've actually productized something based on it. There is this Pix-to-Pix technique, and I'll show you that in a minute, where artists can just play with a bunch of things, create a bunch of outlines, and get a very creative set of outputs. It's also used in medical imaging to convert things from MRI to CAT and so on. So let's look at each of these. So, and I'll show you this tool online. I'll post a lot of the links of the various videos and other stuff that I'm using, which they refer to in the lecture, but you can draw an outline of like a toaster oven and then get a CAT texture imposed on it, various objects with, this guy has played with and created. So all of this is very cool kind of capabilities in the hands of artists to generate a bunch of things and let their imagination run wild. This is some very cool black and white to color conversion. And you can see that it just does a remarkable job of portraying the color. And you have to keep in mind that this is all, computer generated, not a human artist sitting there and saying, oh, let me figure out how to make a color version of that. And the bird seems to be remarkable conversion. So is it with this stuff. There's something about structured prediction with respect to eyes and minute details that apparently these techniques can get right. How artists use it, how it's used in the medical field, that you can there are a couple of papers here where it talks about taking an MRI, which has a lot more detail, and then going to a CT scan equivalent stuff. And this is an input MRI, you have a generated CT, and then you have a ground truth CT of the same thing where an actual CT scan is taken, and then you can compare, and it seems to do a very good job generating a CT scan, very much like the actual ground truth CT scan, which I thought was very cool. Practical application instead of just playing around with converting faces and things like that, if you will. But on the other hand, those techniques are useful as well for game designers and a variety of artists who are creating. This is, and we look at the video for this, is you can generate people, and this is kind of the deep fake thing with just one sketch of an edge, and you can generate a variety of people spaces, just that edge generated. So multiple outputs for edge to edge. All that enabled by the pix-to-pix paper and the concepts and the details. The key concepts we have touched on, but there's a lot more detail. And then we look at, as I keep repeating the video, there is, you can superpose a ballet dancer source video, detect the pose that the dancer is striking, predict the pose, and then impose it, if you will, on the dancer. And funnily enough, this apparently is the grad student who made and developed this app, Everybody Dance Now, and apparently, at least at the time when there's a UC Berkeley grad student who developed this application and hosted it on iOS, which apparently is like a very popular app. That is, you can take a source video and have yourself dancing in sync. Obviously, this is a completely generated image, and this is not real at all. And then the same thing, NVIDIA has come up with this thing called GAN, where it's a semantic representation. So this is just a sketch like I would do if I were asked to draw any kind of natural thing, meant to be a lake, meant to be a mountain, meant to be hills, blah, 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 meant to be trees. And what you get is this photorealistic image. And we'll look at the video for this. Right? And we'll get to this concept a little bit later of actually training a reinforcement learning. So people like Arto and Mayank can probably relate to this a lot better, but training an agent, a reinforcement learning agent, and then bringing in the concept of GANs and combining GANs and reinforcement learning to train an agent to be able to paint. And we'll look at that. Okay, so that's a bunch of applications now that we have talked about. And we'll now stop, and I'll try and get to sharing my other screen, which has the videos that we will get back. Let's look at, so can you see my screen?
Mm-hmm.
Okay, so you can see here, this is just, drawing various cats and making the pix-to-pix generate the texture of the cats. This is just an ongoing demo called Edges to Cats. So apparently you can play with this online. If you like it, you can go get some cats and see how they turn out. Similarly, this guy, and again, I'm not going to play the entire video. I'll just kind of forward through it, and I'm not going to have the audio playing, but basically you can see how designers can use this. Here is a rough sketch of a handbag, and look at what it generates. I thought that was pretty cool. So you could potentially, and then, these designers, they kind of play and generate their own version of it, if you will. And this guy does his own handbag online. And, it still is, I think, stuck on the cat texture. So you can kind of see a variety of things that it does, multicolored pocket flap and all that kind of. So you can play online with various, here's the second guy doing a different. Okay, so we'll switch the other application that he only refers to in class, but and I mentioned it as well, is being able to map videos from each other. That is, you generate a video and you map it to a different context. So you go from a source context to a target context. So for example, if you have a video of a car that's going through a lane and the lane has trees, you could convert it to be a different car, and the trees can be converted to buildings, as you'll see in this video. And obviously, there's a lot more to it than the simple little pix-to-pix concept that we discussed, but because it's a video, but you can kind of, at least it just points to these different applications, and you can kind of go and look at the details. And he talks about in the video, as we go through the rest of it, he mentioned this is the face to edge to face. So you have an input, you get the edge from it, and then this output is not that of a real person, or it could be on a completely different person's face. So this is where you get into this kind of deep fake type of thing. You can get a person, once the audio is synchronized and stuff, saying and doing things that they have never said or done in their lives. And this is the beginnings of the body to post body. So this right person doesn't necessarily need to exist. It could, but it's like, the thing is, from the input video of the person dancing or performing some dance moves, you extract the poses, and then you predict the pose onto this person image. And what is fascinating, and they refer to it in the video when you can listen to it, that even the shadows of the person that are generated are consistent with the person in the output, not in the input, which I thought was pretty cool, the amount of detail, attention that they paid to various things. So you can see these people, only the person in the left is actually performing this. The person in the right, if you will, is projected to be performing this. You can see the video here. The shadow as well. And then this is the semantic manipulation stuff that I talked about, where, you can see buildings to trees, trees to buildings, things getting changed from one to the other, different types of buildings, whereas the original has trees. And then you can go back to trees. So that this kind of thing gives you tremendous capability to do a variety of creative things, right? And actually, as he talks about, one of the practical applications of this is with game designers who can now kind of take some video and then play with it to generate all kinds of simulation capabilities. This is the Everybody Dance Now video. And this is the source, this is the target. From the source, they detect the pose. This person is not real. Fairly cool applications. But in the interest of time, I'm going to skip ahead to something that's much faster. And apparently, this is the actual grad student who has developed this application. Student in comp sci at Berkeley. And then I think the really interesting thing is towards the end, very high. Look at the speed of the movement of this ballet dancer and see how well the movements of the source video correspond to this guy. It's pretty impressive. I mean, there's a little bit of jitter and stuff, but still pretty remarkable. And then the Gauguin stuff, where you just sketch some, do some sketches like I would end up doing probably. And, they have these things trained with images, and then you just pick like from a template and look at this is particularly, I thought, a very cool kind of stuff where they just draw this blue thing going from here and out pops the mountainous thing with a waterfall in it. For a guy like me, you can't draw to save his life. And here, they just produce these rocks in the ocean, produce photorealistic images on the right from these crazy structures. And some of the cool capabilities is even the shadows that it generates. Look at this. Shadow of the mountain. And to think that all that is just done from training images and not by something sitting behind it, actually painting. Fascinating. And again, this is something from a video, and this way he talks about the usage of that in the video games to create some kind of simulation environments. Okay. Time again will skip, but it can produce an amazing number of just phenomenal and really pretty pictures. And then this learning to paint thing. Yeah, so here, what this paper is apparently from the DeepMind guys. And what it does, this guy, yeah. So what it does is it actually apparently, there's a whole blog post and things you can play with and so on. But what it does is this particular paper is making an agent learn how to use kind of a drawing software, if you will, or a graphic software. And basically the agent is learning to manipulate that software to produce the results that we seek. So it's as if, some human, in this case an agent, is painting the image using rendering software. So there's a policy that the agent is learning and actually implementing the policy. And that's kind of what is going on here. So for example, as it says here, this is all abstractions, but I'll pick one which is more of a reconstruction oriented thing. So let's say we pick this guy. So on the left to play it here. So once I pick this, then it will generate some version. And again, it's not exactly the same because obviously it's an agent that's doing it, but you can see what happens. That's really very application where an agent, and it's doing this through the combination of GANs and reinforcement. So that's kind of what is going on here. A lot more detail. Obviously, this is more, and then you have increased realism, some styles that you can create, and then this is just basically reconstruction. But so the idea here is you take the face and then you render it as if an artist would have rendered it, and there is no real artist. It's just a reinforcement learning agent that's learning and applying the inputs to the renderer based on some policy that it's picking up, which I thought was again very cool. So we've seen a tremendous number of variety of applications for GANs. And that's one reason why I believe that research into GANs has exploded over the last several years, at least until 2019. I haven't kept track of it in the last. Anything else that's in this space, minds that you're familiar with that's very cool? Okay, so I'm going to stop sharing and switch back to the PDF. Let me know when you can see that. Can you folks see my PDF?
Yep, can see
Yes,
it.
no?
Yep, yes.
Okay, thanks. Any questions on what we have covered so far? I mean, it's a lot of just illustrations of practical things, but there's a lot more papers to go through, and probably we'll get exposed to a little bit of these in the homework and the Colab notebook reference implementation. Any comments or thoughts before we move on? No? Okay, we'll keep going. The last section that he covers, and this is kind of the last part of the lecture, the remaining stuff we'll cover next week. That Peter covers, this is something that one of the TAs, teaching assistant, covers. Something, this part is using GANs. We've used GANs for a variety of techniques so far. Here we are using GANs to learn the representations of the images, and in this case, mainly it could be anything, but in this case, we are focused on images. And he mentions the part that we haven't yet been formally introduced, if you will, to the details of what is representational learning. But he says, at a high level, think of it as learning to represent what is in the images, and think of it therefore as kind of learning a latent representation, if you will, of some data such as our input images. So that's kind of what we are after, right? And there are two ways this happens. One of them, two techniques, at least until the time they presented this course. One is called the information maximizing GAN, or InfoGAN. And the second one is called BiGAN, which is a bidirectional GAN. And those are the two papers that they discuss. Again, not in very great detail, but at least the key concepts covered in each of those two papers. So let's first focus on InfoGAN and what it does, and the key concept GAN. So the first thing, let's look at a MNIST digit, right? So what do we have in an MNIST digit? Basically, it's a representation of a digit. So it's just a sequence of numbers with bit values and so on. So one of the things we could think of is we could think of the data as being represented by some simple factors, such as we would like to know the class of the image. So, obviously in this case, we have 10 classes from 0 to 9. And so in this case, the class is, let's say, 5. We'd like to know, let's say, the rotation of it, meaning is it slightly tilted to the right, to the left? Then is the width of the stroke that is used to indicate it, the number, if it's, light, thick, medium, and so on. So these are various factors that represent the class, the rotation, the thickness of the stroke. These kinds of things are factors or variables, if you will, that describe the image. So we can think of those variables as kind of a latent code in addition to just the raw data. So what we can, if we, and maybe some of you are much more familiar with the graphics space, but in a graphics, if you, in a graphics pipeline, if you provide the renderer, that is the thing that scans the image and creates it, if you will, for display on the screen, then, if you give it a shadow, the lighting, the pose, and stuff like that, it's able to render the image. Those are various parameters that you would provide to the rendering software, and the software will then give you the output of that image. That's how the renderer works. So in some sense, what we are seeking with the InfoGAN approach is to, given an image, let's try and generate the inputs to a renderer that would end up rendering the image that we are actually seeing. So for example, if we have a 5, the MNIST digit 5, if we can give a code such as, the thickness, the orientation, and the class, then we would, these inputs to a rendering software, then it could render a 5, right? So in essence, conceptually, what we are trying to learn from the representation learning part of this InfoGAN is to develop a representation for the MNIST digit, which would go into a renderer and give us the output that we are seeking, right? And typically, this kind of a view of learning the representation is also apparently called inverse graphics, because you can think of if graphics pipeline is something that takes you from a renderer input to a renderer output. What we are actually trying to do in this case is to say, given an image, what would have been the input of a renderer that generated this image? That's kind of what this method tries to get at. That is, given an image, what input to the renderer might it have been such that we get this input, right? And in fact, many people say, think of even the whole computer vision field as kind of inverse graphics, if you will, right? Or as an inverse graphics problem, because all of computer vision is trying to understand what the generated images are, so what the output of the renderer is, and so we can learn what the input might have been. So the InfoGAN then is how to generate something like an input to the renderer, but do that using our GAN structures, right? So in order to do that, what we then set up the InfoGAN as is, in addition to the traditional GAN, which is up, all the way on the left of this image up to noise. That's all our traditional GAN setup: generate noise, go through a generator, give it the input thing, give it a discriminator, and then tell us, hey, is this real or is this fake? But in addition to this, the InfoGAN approach says, oh, but since we want to generate the input that would be going to a renderer, let's also provide a code in addition to the noise, to the generator, in addition to this guy, right? So what that then does, now we have seen it in multiple instances, that if we provide more information to the discriminator, it does a better job in those realms as well of discriminating. So given that, what it then this kind of a setup enables us to do is, in addition to the discriminator deciding real or fake, it also enables us to seek out some of the independent factors that are driving the distinction between the various images in the output, right? So it enables us to capture the particular digit, how is it rotated, the thickness of it, and so on and so forth. Now, how do we do that? One kind of obvious way we have touched on earlier, even in this lecture, is to use this concept of mutual information. So the point is that you capture in this code mutual information that is present in your image as well. So the independent factors that are there in the latent code, that is in this code guy that we saw here, should capture maximally the variations in the generated images. So in this case, what we're after is maximizing the mutual information between things that we have already seen before. What mutual information equation is, the X is the output of something that's generated from the latent Z. We also provided a code, and then you get the X, right? So again, we go through the similar, and by now we have seen this the second time even in this lecture, you kind of see the equation of maximal information between the code and the latent and the code combination, which is the output of the generator. You go through the equation, you make it a scale divergence and reduce it to this form, which is what makes this a variational lower bound. And what this means is that this equation essentially is converting the equation here into kind of a double expectation. And one expectation is that of predicting the C prime, that is the code that produced the particular image. So this is the thing that I was referring to earlier, which is, hey, we want to learn the code that would have gone into the renderer in order for it to have generated the rendered image, averaged over all of the different C primes, that is the codes, and average over the various X's, that is the various images. And this particular inside bit of the equation is nothing but a maximum log likelihood for an excellent classifier or a good classifier. This is something we've seen multiple times by now. So it's just this good classifier average over the codes, average over the images. Practically, all this math just leads us to that conclusion, which is what then we go ahead and implement in the stuff. So basically, it is a traditional GAN. The info GAN, what it does is it takes the noise, but it also does the code, goes through G, Q, and what's the code. So basically, we want to generate a code, which if it would have gone into, would have generated the rendering image. So it's the loss that predicts the code given the generator output of the Z and the code. So that's kind of what we do, right? And another way to think about it is that if we maximize the mutual information between the latent code and the generated image, which is kind of what we are doing by this setup and by these equations, if we maximize the mutual information between the code, right, the code and the generated code from the latent. So that's kind of what we are maximizing. So if we maximize that mutual information, then what we are saying is, for example, if the MNIST digit is a 1, then the class has become a 1, right? So there is no uncertainty with respect to class. If it has a particular rotation angle, so if we reduce that entropy, then that means we can now know the rotation. If we know the thickness, and we are reducing entropy in that direction. So by maximizing the mutual information, we are reducing the entropy. That means we are reducing the uncertainty in what that image is. So we are able to recover the code from the actual image with minimal uncertainty, right? So that's another way of thinking about it. And the more we do this optimization, apparently, the more, the better our codes get. And the other fascinating thing about this whole InfoGAN approach, which I thought was pretty remarkable in eventually what it results in, is the ability to disentangle the various latent variables. So he introduces this concept of disentanglement in machine learning. And apparently what disentanglement means is if you have a bunch of latent vectors for explaining a particular value of an image in a data set, then the disentanglement means that the measure by which the various latent vectors you can think of are independent of each other. That is, that if you vary one latent vector, then one particular aspect of the image is varied. Now, to the extent that they're entangled, then if you vary one, multiple attributes of the image change. And therefore, you can kind of grasp intuitively why disentanglement is a good thing we would want, because that means, for example, in a phrase, if you were to vary a particular latent, that will vary whether or not a person has glasses or whether or not the person is smiling, certain specific attributes without changing a bunch of other attributes. So the more disentangled the latent vectors are, the easier would it be for us to manipulate the image to get it to where we want it to be. So that's something that this InfoGAN approach apparently provides some excellent results with. That is the ability to get disentangled latent vectors, which when you vary can then vary specific attributes. We just goes into the thing, and obviously since we kind of contributed with just a shared connet, these things are easy to compute. So it's InfoGAN is easy to implement, relatively speaking. And this slide and the next one are some fantastic illustrations of this disentanglement concept. So here, as you vary the code, you see that what changes is the class remains the same. So it's this object. So if you don't vary the Z, your class of the object remains the same. It's just that the pose changes. You can see that it's changing its pose from facing straight towards us to kind of facing in the diagonal direction. Now, as you move the Z or you vary the Z, you begin to see different chairs. But as you vary the C1, which is say a particular value of the code, then that begins to change the orientation. So same thing for all these different classes which you vary by varying Z. Then here, C1 prime, which is a different attribute of that, and that in turn is beginning to change. So as you vary that, you vary the size of this method or a particular chair. You can see that the size begins thinner and thinner, right, in each of these images. But as you vary the Z, the type of chair that's there varies. So that's kind of a very cool result of this InfoGAN paper and its implementation. And again, he says, look at, you can do that as I illustrated with emotion. And, the Z variation here is different people. And the C1 variation is like smile aspects of it. And then here it's presence or absence of glasses. So, what is cool about this compared to even the original DC-GAN that Mochen had gone through last week is the fact that with InfoGAN, the latent variables are capturing different aspects of your data set. And I think that is, as he says in the lecture, also a very elegant thing that it's able to do. So the most important thing about an InfoGAN compared to the earlier implementations is the fact that the latent variables that InfoGAN pieces out are disentangled representation, and they learn it within the context of a GAN setup. And the one other study they did was to see, okay, this is all done at fairly low resolution, small images, but does this scale at the level of very large images, at the scale of ImageNet? So ImageNet, obviously MNest is 10 classes. ImageNet, on the other hand, is 1,000 classes, right? So that led the researchers in the direction of using big GAN, and then the net result, to be a spoiler, is to say, yes, it does work. And the way it works, though, is through the second technique, or the last thing we learn in this portion of the class, which is big GAN or by big GAN. And again, he doesn't go into the nitty-gritties of the implementation, and he warns multiple times that it's fairly complicated in order to get all of these things right exactly where we want it. So it's not a simple thing to achieve this, but it's important that we do understand that it scales, and we are able to apply the bidirectional GAN or a big BiGAN to get the results that we seek. And we'll look at the big or the results of the bidirectional GAN and what's the basic concept in a minute. But what we take away from InfoGAN before we move there is that GANs have this property, as we have seen now multiple times, that if we feed it some additional information into the GAN setup, like in this case, we are feeding the code, then the GANs automatically factor that into the implementation. We saw that in Pix2Pix when we kind of added the input image in addition. Like, so for example, the X got added to the GAN loss equation, and we also added, if you will, the lambda L1, which is more of the quality of the output image. But in this case, we're adding a code to the basic GAN setup. So in this sense, we are modifying the basic GAN infrastructure setup that we have to get the GAN setup to do a bunch of more interesting things that we want it to do. And so the key thing to take away, he says, because obviously this is a class orienting people towards future research projects, so it could be interesting to any of us too, if you want to play with this, is, hey, keep in mind that GANs tend to jointly and intuitively jointly optimize some additional information that we provide to it. And it automatically factors it in when the optimization is done. So therefore, you can, kind of think of what other things could you be potentially providing to it. So here he just says, hey, the scaling is possible if you do that with big GAN. It's not, it successfully does that, not just for the 10 MNIST classes, but even in the case of something like ImageNet. And then the last concept is this idea of big BiGAN. So it's big BiGAN. We'll discuss why bi in a minute, but it's basically big GAN with some variations thrown in. So what is the fundamental concept of bidirectional GAN? So, in a GAN, we've seen in a basic GAN, if you ignore the left half of the left side of this picture and just look at this part, that's the basic GAN setup, right? You have the Z, which is essentially a Gaussian, you take it to the generator, and you obviously create a generated image X prime, whereas a real image is X, you can think of a generated image as X prime. So if you look at the right side of what I've sketched here, typically we go from Z to an X. Now, recall that in an encoder or in an autoencoder, which encodes the encoder part of an autoencoder encodes X into a latent, right? So we go from X into a latent. So when we want to use GANs in order to do this thing called representation learning, then what we are actually interested in is getting the representation from the X. So we are interested more in this dotted line direction than we are in going from Z to generating X. But what's the point of generating Z? The point of using the encoder after we go from X through the encoder is to get a vector which we can then use for downstream tasks, such as classification and anything else that you may want to do as a downstream task once these encoded vectors are generated. Okay, so these are the two concepts to keep in mind when we begin to apply this concept of bidirectional GAN. So what we want is to have an encoder that takes in your X and generated the latents, right, that you can then use for the task. So the idea of a BiGAN is simply to implement that. So just like in G takes Z, goes to X prime to take a latent Z, which typically in a basic GAN is nothing but a Gaussian input and goes to a generated image. Here we take X and go to Z prime, okay? And so we saw in the pix-to-pix kind of stuff that when we fed more information to a discriminator, then the discriminator ends up doing good things. So here, what we end up doing is after putting the X through the encoder and getting a Z, we combine the X and the X prime. So this X is the actual image, this X prime is the generated output of the generator. So the real and the generated. And then we take the encoded latent, that's the Z prime, and then we take the Z, which is our sampled latent, right? And we feed those to different parts of the discriminator. And as we'll see next, there's a little bit more detail about this, but obviously a lot more detail in the actual paper. And then we get the discriminator to say, hey, is this real or is this fake? And the interesting thing about it is you go about this setup, implement it on the ImageNet level of images, do the unconditional image generation, lots of images, big images, and a tremendous amount of compute. You end up with very good samples on the output of the discriminator. And what's fascinating is that these are all unconditional. Right now, the big GAN is conditional on the class. And in this case, the thing is, it's pretty much the same, the sample quality, but without any labels, which means that the encoder in this diagram that we have is actually learning very good representations of X as a result of this entire GAN-like setup. So, you see the quality of the images is pretty good. And how do you judge, though, of whether your encoder is learning good representations? What do you measure as the quality of the representations that the encoder is learning in our setup? So one of the ways that he talks about doing that is whenever we get the output from the encoder, what we do is we stop gradient it. We can basically freeze those weights, stick a linear classifier on top of it, and see how much a very simple linear classifier gives us the classification of those images into those classes that we actually know, right, what they are. So that tells us how good are the semantic features that the encoder is learning as part of the representation learning aspect in this kind of a setup. So if we do that, and again, keep in mind that we are here again generating duals, if you will. So in one direction, we are taking the latent sample, which is just a Gaussian, throwing it through the generator, generating an image. The other direction is taking a real image, going through an encoder, and then generating a predicted latent. And then we throw both the predicted latent and the indirect latent Z, and we take the actual image and the generated image, and we feed that through the discriminator setup, much like this. And so the discriminator now is discriminating between pairs, between the actual image and the encoded image, between the sample latent and the generated latent. And we do that, and we feed this, and these are just unary, meaning they just focus on this, and this J term within the discriminator is what combines these two tracks or channels, if you will, and do the loss. Don't know the details of how the loss is set up, but do all that, and what you get is what you have. This structure is what is referred to as big bidirectional. The bidirection comes from because you're going from latent to X and from X to latent, and you feed both of the pairs through a discriminator network, which is our setup for the GAN. And here's the fascinating part, and I was actually quite impressed. What you see if you stick a classifier, a basic linear classifier, on top of a big BiGAN, which is, there's a paper on big BiGAN, probably prepared by this guy, but I'm not 100% sure of that, but you can go refer to it. You get a result, top one result on ImageNet of 61.3. The amazing thing about it is the corresponding number for fully supervised is 76. So obviously we can say, hey, this is nowhere near the 76 that you get in supervised. But keep in mind that this is completely unsupervised, right? That if you're not telling this whole process what the heck the classes are or anything, and it still gets you with a pretty basic classifier to a 61.3% top one accuracy. I thought that is pretty remarkable. And the other thing that they point out qualitatively, that's a quantitative result of how good your representation learning is. Here is a qualitative example. These images on the left are the anchor images. And then if you do a nearest neighbor search in the latent space that you're learning, and then ask the network to generate an image based on that latent, which is the nearest neighbor among the nearest neighbors of this latent, look at the quality of the images that it relates and how close it is to the class of the original image. Again, that's a fairly remarkable illustration of the fact that your encoder has really learned the representation very well of that class. So you can see a dog breed, and you can see there's so much similarity. Again, here, snow and mountains, an RV, and various RVs. So this, I thought, was again a very highly illustrative, qualitative representation. Of course, the numbers back it up by that result. And then here it just says, hey, if I give you this image and then ask you to produce a reconstruction, here's a chimp or a gorilla, and here, is generation of it. Here's a person, you see trees, snow, it generates the same thing. This is fairly remarkable. You give it a pizza, it generates a different kind of pizza. All on its own, not supervised at all. I thought that is pretty interesting. Same thing, other examples. Okay, that's it for today. Any questions? Next week, we'll kind of cover the remaining, and it's, I believe, a lot more theory. Yeah. Any questions? If not, then let me seek volunteers for any of the homework, collab, or open sessions. people have dropped out with changes in schedules and times and things like that. So if any of you would like to volunteer to lead any sessions down the road, please do so. With that, I think we are done for the day. Thanks for joining us.